Alright class, I thought I'd pick up where we left off on the last video. So we're in chapter 13 on physical properties of solutions, and what we want to focus on today is talk about what drives a solution to dissolve, and also concentration units. So that's what we're going to focus on. So just kind of refresh your memory from the last video. Let's see. So we said the delta H of the solution, so the heat of the solution, and that is when a solute dissolves in a solvent. So again, what we're talking about here is we have a container. Here's our water, and we're adding a solute to this water, and if the reaction or the process happens, this solid then dissolves into particles within the solution, in the solvent, and we have a solution. And so that the heat of this solution is equal to how much heat is required, or the enthalpy, if you want to use the correct term here, the heat of that's required to separate these solute molecules or atoms, and then the heat required to separate the solvent molecules, so that there's space there between the solute, breaking the intermolecular forces, and then the heat of the mixing of these solute and solvent particles. And so if the if the overall heat of solution is negative, that means that we have an exothermic reaction, and that means it's giving off heat. The container is going to get warmer, and that generally leads to a favorable mixing, because it means that if you think about the process, if we start here with what our initial substances, and we end up with a product down here, we're in lower in energy after the mixing has occurred, after we make the solution, and so the ball tends to roll down the hill, right? So we know that's spontaneous. But there are processes that occur, like ammonium nitrate dissolved in water, that the process is endothermic. That means you initially start here and you end up here. So there is an energy deficit that we have to make up for, and that energy comes from the surroundings. And so if you had a beaker of water in your hand and you added ammonium nitrate to it, you'd actually feel the beaker getting colder as the ammonium nitrate dissolves in the water. So it's an endothermic process, and you go, well, how would that happen spontaneously? Because we know we don't see the ball roll up the hill, and that doesn't happen spontaneously. So there must be another factor that makes this reaction or this process happen, and that's called entropy. And entropy, another name for that is just disorder. So if you don't like the word entropy, just think of the word disorder. And so we can see once a mixing occurs, there's more disorder in this process or in this outcome than if we leave the ammonium nitrate as a solid surrounded by the solvent water. So entropy is going to be a major topic of Chem 180. We're going to visit it multiple times this semester, but it is a driving force for processes, and it's also a driving force for chemical reactions. So entropy of a system is a measure of the diversity of the ways it can store its energy. So what they mean by this is, if you look at the container and you say, okay, here's my water and here's my solid. If I allow if the solid dissolves in the liquid, I have more places for the solid to occupy than this little triangle here. So that's diversity of ways. And so there's more. What they're really kind of bending here is they're trying to get you to think about statistical analysis, that there's much more varied probability than possibilities of positions than in this diagram here. So that's what they're wanting you to think about. Later on, we're going to talk about using statistics to describe why reactions happen based, and it's entropy, but they're going to use statistics and positional, the number of possibilities of positions to show how entropy works. So systems change in such a way as to increase their entropy. I mean, think about it. When you wash your clothes and dry them, if you don't fold them up, it takes energy to fold them up and put them back in the drawer. And if we don't do that, then the clothes start flying all over the place. And so that's entropy. That's entropy. Things tend to move towards disorder. It takes years to build a skyscraper, but they can be brought down fairly quickly because it increases the entropy to go from that orderly shape to a disorderly shape. So that's what we're looking at here. So generally, systems with higher entropy have more mobility. They have a greater range, like we see here. Things with lower entropy, particles are confined. Just think about the difference between a solid and a liquid that it has a particular volume. It takes up a certain amount of the container. It doesn't take up all the container. And then we have a gas, and it takes up the entire volume of the container. And it has more entropy than the liquid or the solid. The solid has the least amount of entropy. It's very orderly, tightly confined, immobile. So just think about it for a minute. Think about what you think entropy is. Make sure you have a good feeling and knowledge of what entropy is. And it's easy. It's just disorder. Think of it as a disorder. Less entropy, less disorder. All right, so when we talk about solute particles, relatively mobile in a liquid solution, whereas the crystalline solid is not. So again, we're getting back to our picture here. Here is the crystalline solid. Here's when it's dissolved. All the particles have a lot more mobility and places to occupy. So when we increase, the increase in the system entropy promotes dissolution. So more entropy in this is the entire system. This is our system, what we're focusing on. The more disorder, the more likely we're going to have dissolution. All right, and then it says substances dissolves as long as the entropic encouragement is stronger than the endothermic discouragement. So what we're looking at is the battle between enthalpy and changes in entropy. That's where what we're looking at. So if the entropy is positive, that means greater disorder, and the reaction is exothermic, those reactions are going to happen. The ball's rolling down the hill and we're getting more disorder. That reaction's most likely, that reaction is going to happen 100% of the time. All right. If the reaction's endothermic, and so it takes energy for it to dissolve, then we have to hope the entropy is greater than this value of change in entropy is greater than this positive value or the endothermic value for delta H. For that so that the entropy, the disorder, overcomes the endothermic process. So that's where we're going with this. So I think I've beat this with a dead horse. So you can read these other slides here. I do like this slide. It just shows you that there's more order here and here. And if we remove the barrier here, these gases are going to freely mix together because there's a lot more disorder. There's a lot more positions for each gas, molecule, or atom to occupy. And so we see definitely big increase in entropy and the change in entropy here from start to finish. So if that dominates over delta H, then this reaction is going to happen spontaneously. It's going to happen as soon as we take this barrier away. It's going to happen. So just keep it in mind that entropy is a big driving force for this reaction. So ammonium nitrate, again, what's going on? You have the ammonium nitrate in water. It's first a solid. As it dissolves, entropy increases, and it requires energy to separate the ammonium ion from the nitrate ion. It takes energy to separate the ammonium ion aqueous dissolved in water and the nitrate ion aqueous dissolved in water. So that separation makes this, because there's a fairly strong chemical attraction between these two ions, or intermolecular force, if you want to think of it that way. The delta H for this process is positive in value. It's an endothermic process. But the entropy is so great, it makes up for this endothermic process. And that's what they're getting at in this slide and the next slide. All right, let's move on to the next section. So this section is really important because we're going to learn about concentration units, and you have to become fluent in these concentration units because we're going to be using them from here on out. Once we get through this section, they're going to assume you can do concentration at all times, and you shouldn't spend that much time on calculating concentrations. You're going to spend more time on the concept that we're covering and not just calculating the concentration of the solution. So this is a really important chapter. You got to do lots of problems, get your system down of how you're going to calculate concentration. What does concentration mean? So we actually have defined concentration in Chem 170. It's the amount of solute divided by the amount of solution, or the amount of the substance you're interested in divided by the total amount of materials. That's another way to think of it. So for us, the most important concentration unit is actually molarity, and let's just refresh our memories of what molarity is. It was talked about in Chem 170 when we did solution chemistry. So let's just refresh our memory what molarity is. This is the most important unit for most chemists. Its symbol is a capital M. That's how you know it's molarity. And sometimes you'll see an underline under the capital M just to emphasize that it is capital. It is moles of solute divided by liters of solution. And remember, solution is not just one thing. The solution is the solute plus the solvent. So we need to know what the total volume is of these two things combined, and that volume is measured in liters. So moles of solute divided by liters of solution. We're also going to be talking about mole fraction, and mole fraction, I think the best way to do mole fraction, let's just draw a picture here. Let's say I have a container, and in this container I have 2A molecules, and I have, let's say, 4B molecules. Let's make it 5B molecules. And I have 3C molecules, all right? So I have substance A, substance B, substance C, and if you remember, when we did gases in Chem 170, we talked about Dalton's law. It said the total pressure is equal to the partial pressures of A plus the partial pressure of B plus the partial pressure of C. Well, mole fraction is related to this, actually. So what we have here is, if I want to know what the mole fraction of A is, I have 2 particles of A, or 2 moles of A, I should say, because we're going to be working with moles. 2 moles of A divided by a total of 10 moles of total. All right, 2 plus 5 plus 3 is 10. So the mole fraction is 0.2. So mole fractions can only be, 1 is the greatest the mole fraction can be, and 0 is the least, all right? And so if you want a mole fraction of 1, you'd have only A in this box. It'd be 10A over 10 total moles, and you get the number 1. So it's important that you know that, because you're going to exploit this. If you only have 2 particles in the box, all right, or two substances, let's say that, and you have the same amount of each, or whatever, it doesn't matter what. Let's do it this way. We can do it this way. Okay, so we got 3 B's and 2 A's. All right, if you know the mole fraction of A is 0.4, Then 1 minus 0.4 tells you the mole fraction of B is 0.6. All right, so that when you add up the mole fractions of all the materials in the container, it has to equal 1. So you are going to exploit that. 1 is unity, that's the entire box, and then you subtract off the amounts of each substance. So if it's 2 substances, 1 is 1 minus, you got X for the amount of substance that you know, and then the other substance has to be 1 minus X. So you're going to use this. I think there's a homework problem where you have to know that in order to solve the problem. So keep that in mind, that we are going to use mole fractions, and we're going to use it to solve. And we've already seen it, actually. If you remember this, I don't know, it depends how your professor in Chem 170 taught in General Chemistry 1, but partial pressures and mole fractions kind of work hand in hand. And so we were introduced to this back when we talked about gases. All right. Let me say one other thing about molarity before we go on. It just reminded me to do that. Remember that volume is temperature dependent. If you remember about gases, we saw that volume is proportional to temperature. So as the temperature goes up, the volume goes up. So if you measure the molarity at room temperature, and then you measure it at, let's say, 90 degrees Celsius, the temperature went up, the volume went up, so the liters of solution is going to go up, and that's going to make the molarity less, because as the denominator gets larger here, this is an inverse relationship, the molarity would be less. So molarity is temperature dependent. That is one of the weaknesses of molarity, but most of the time you're working in the lab, the temperature isn't fluctuating wildly. And so molarity, if we're mixing one solution with another, molarity is a good unit for concentration. But if you do work with a large range of temperatures, then molality gets to become a really important concentration unit. Still has the moles. You know, why are the moles so important? Because when I write a balanced chemical equation, it says 2 moles of hydrogen reacts with 1 mole of oxygen to form 2 moles of water. So we're working in the realm of moles here. So we want moles in our concentration unit to make it easier for us to relate that to our balanced chemical equation. So molality, how do you know it's molality? There's a couple of things. First of all, it's a lowercase m, not a capital M. So be careful between capital M for molarity, lowercase m for molality. And it's the moles of solute dissolved in a kilogram of solvent. A kilogram or 1,000 grams of solvent. So notice it doesn't say solution here, it's solvent. You go, when would I ever use this? Well, metallurgy uses it because it's temperature independent. Notice there's no volume here, so it is temperature independent. And the other thing is that, let's say you've got ice on the road, and you want to know approximately how much salt you need to put on the road for the ice to melt. That's a molality equation, right? You kind of estimate, if I've got an inch of ice here, I can figure out what maybe the mass of that is over a certain amount of road, and then I can determine how much salt I need to add so that when it dissolves, I'll have a molality here. And then that'll tie into colligative properties, which we'll talk about this semester, like freezing point depression. So that's when we get to freezing point depression, you'll see why salt melts ice. So that's where we're going with this, and that's, like I said, this is kind of the toolbox of what we're going to use the rest of the semester. So you have to become fluent in these concentration units: molality, molarity, and then we'll talk about percent concentration. If you really have problems with this kind of stuff, just make you a mnemonic. What's a mnemonic? It's a memory device to help you remember how to solve these type problems. Put you a triangle, put you a T in the triangle like so. Molality goes here. Moles of solute go here. Kilograms of solvent go here. So if I got the moles, I divide by the kilograms of solvent, I'll get the molality. If I know the molality, I know the moles, I can tell you how many kilograms of solvent I need. So use the triangle there if you need a mnemonic to help you remember how to solve these problems. All right. So the next concentration unit is percent by mass. A lot of engineers use this, biologists use this, because the whole thing about percent by mass, which is really nice, two things. One is it's temperature independent. Notice there's no volume here. All right. The other thing is I don't have to know what the chemical formula of the sugar is or the water. I mean, it's just the mass of the sugar. I don't have to know it's C6H12O6. I just need to know what the mass is. So I don't have to know molar mass and conversions and molar mass into grams. And that's why people like percent by mass. And then I don't have to know what the, I don't really have to know what the chemical formula for water is. I just need to know what is the mass of water I'm mixing with it. So percent by mass is the amount of the solute in mass and divided by the total mass of the solution. So it is solution. It is the solute plus the solvent. What is the total mass of the solution? So the trick here, I think what causes students to have problems with this is they'll say, okay, you've got 50 grams of sugar, and we'll just say GLU for glucose or something like that. And and then they'll say it's in 150 grams of solution. 150 grams of solution. And here's a question they ask all the time is, how many grams of water is in this solution? Well, it's, 50 grams is the solute, the sugar, and the total is 150, so that means it's 100 grams of water here. So that when you add these together, you get a total of 150 grams of solution. So just be careful there. So 150 grams of solution, but sometimes they ask you how many grams of water is required for this solution. And I just see that throws students off. And you can do this because mass, you can say the total minus the mass of the solvent or mass of the solute will give you the mass of the solvent. So just be careful with that. The other thing people like about percent by mass, if I want to make it, this is also called pph, which is parts per hundred. But if I change this to 1,000, multiply by 1,000 instead of 100, it's called part per thousand. And then when we start talking about environmental pollutants, a lot of times we multiply this by a million. So if we multiply by a million, which is 1 times 10 to the 6, we call this a part per million. Or if we multiply by 1 times 10 to the 9th, we call it a part per billion. So some things are really, really small, shouldn't be in your water at all, hardly, and so that would be measured in parts per billion. Other things can be in the form of part per million, and some things are we generally don't say part per hundred. We do say part per thousand, but generally when we just say part per hundred, we're just going to call it a percentage. So just keep that in mind. We are going to use all of these units, and you are going to have practice converting from molarity to molality to percent mass, and then parts per 100,000, million, or billion. So there's going to be plenty of problems for you to manipulate these concentration units to become fluent in writing concentration and calculating it. And the reason why we have all these different units, depending on what your field of science is, you're going to be couched in one unit more than another. For chemistry, it's molarity, but metallurgy, it may be molality, and for environmental science or ecology or things like that, it may be parts per million, parts per billion. All right, so what I want you to do here is I want you to read this, and I want you to try doing the problem on your own. Don't look at the other pages. Start with this page here and see if you can solve the answer. So read this, stop your video, work it out on your own, and then let's see if you get the correct answers. If you get the correct answers, then you're good. You understand what we've covered so far in the class. If not, then you got to go back and look and see what you're missing. And then if you're not 100% confident, try to do some of the odd problems in the back of the chapter. The answers are there available for you. You've got your homework problems too, but You've got to become fluent and proficient at doing concentration units so it's not holding you up on an exam or a quiz. So this one says, so we stop here, and then I'll come back and we'll finish it. All right, welcome back. So this says a solution is made by dissolving 170.1 grams of glucose in enough water to make a liter of solution. The density of the solution is 1.062 grams per milliliter. If they don't give you the density and it's mostly water, you're going to, just something to refresh your memory here, the density of water, if they don't give you any density for solution, then we're going to assume, because the solvent is water and it's probably a small percentage, we're going to say, just remember that if we always assume density has, the density of water is 1.00 grams per milliliter. If not given, that's the assumption that we make. Okay, just something to keep in mind. May not be required for this problem, but just keep that in mind. All right, so the first one says calculate the molality. All right, so molality is lowercase m equals the moles of the solute divided by the kilogram, 1 kilogram of solvent, or kilograms of solvent. We're going to make it unity, so we can do that. All right, so the first thing we have to do is, you can see we got to convert this grams of glucose to moles of glucose, and you got to calculate the molar mass of the glucose. Now that should be automatic. That you should be fluent at this point in Chem 180. That's a Chem 1, that's called molar mass, right? Molar mass should just roll off the tongue, and you go, oh yeah, this is easy. I just take the 170.1 grams of glucose, and then I know when I calculate 6 times 12 is 72, 72 plus 12 times 1 is 12, so that's 84, and then 6 times 16 is, 6 times 16 is 96. 96 plus 84, yeah, is 180.2. That's pretty close. All right, so 180.2 grams per mole. That's the molar mass of the glucose. So if I multiply that out, I will get the moles of glucose. So I'll have the moles of the solute. Now, the tricky part is, how do we get kilograms of solvent? They don't tell us how much solvent we have. And this is where students get confused. They tell us we have a liter of solution, but they don't tell us the mass of the solvent. So I hope you figured this out, but if not, just stop right here again and think about, how would you convert liters of solution to grams of solvent to kilograms of solvent? So if you can do that, you're doing great. All right? So stop, think about it, and we'll come back to that. All right, welcome back. So you know a liter of solution is 1,000 milliliters. So we got 1,000 milliliters of solution. I'll call it SLUT. Well, let's just spell it out. All right. And then what you know is, you know the density of the solution is 1.6 or 1.062 grams per milliliter. If I multiply this and those cancel out, that will give me the grams of solution. And I see a lot of students use that number for this problem up here. No. This is grams of solution. You need kilograms of solvent. So then you go, well, how am I supposed to get solvent? Well, you know that the solution consists of both the solute and the solvent. So if you subtract 170 from whatever this number is, you'll get the grams of solvent. So let's go to the next slide. They do a much better job at this than me, right? All right, so here, I don't like how they did the division here. I'd rather you do it like I should, which is, write it like 170.1 grams and then multiply by 180.2 grams per mole. That's the system we use in chemistry instead of just they did this to save space. I understand it. So this is how many moles of glucose we have. They took the liter solution, multiplied by the density of this solution, and they get 1,062 grams of solution. This should be a point right there. Oh well, they changed this to liter. Okay, so okay, that's fine. You can do it that way. That's a big step. I wouldn't have done that. But they did. All right. So, okay. So then we have the grams of solution. We both would come up with the same answer here. Subtract off the grams of glucose. That's how many grams of water we have, which is the solvent. And then we convert that to kilograms, because molality requires that it's moles of the solute divided by kilograms of the solvent. And we come up with the molality of 1.06 molal. The other thing here is what's your significant figures. If you're doing Connect homework and you don't write this in the correct number of significant figures, it will count it wrong. And then I get students saying, I'm doing this correctly. I know I'm doing it correctly. I know that molality is moles of solute per kilogram of solvent, and I'm not getting they're saying I'm not getting the right answer. It may be because your significant figures are incorrect. So just keep that in mind. All right, so the rest of these are fairly easy, right? If we want to know what the percent glucose is, we just take the mass of the glucose divided by the mass of the solution, multiply by 100. We get the percent glucose by mass. Again, we like this solution. It's used in biology a lot. You don't have to know the chemical formulas of anything. You've got the mass. You didn't have to convert that to moles. So that's the advantage. And then if you want to know what it is per million, you just multiply. Instead of using 100 here, use 1,000, and now you can write this as parts per million glucose. Out of a million particles, how many of those particles are glucose molecules? So in a million particles, 1.602 times 10 to the fifth of them would be glucose. The rest would be the solvent, right? Or the solution, I should say. The solution, not the solvent, the solution. All right, so I hope that helps. You just got to manipulate these, do lots of them. The main thing here, and I'll tell you what I see the most mistakes. Students don't label this part. They get the grams, but if you don't know what the grams are of, just like I said, solvent there, and it's not its solution, make sure you not just label the unit of measure, but what's it of. If you do that, you won't make careless mistakes. But the people who just say, okay, I'm going to take 170.1 grams and divide it by 1062 grams, they don't know what it is. They don't remember is that the solution or is that the solvent? And so make sure you put your descriptors here. Otherwise, you're going to make careless mistakes there. All right. Comparison, we've really already talked about this. Molarity, it's because we have flasks. In chemistry, we want things in moles. We like measure. We have accurate measurement tools in the lab, like a pipette and a burette and so forth. Molality, the advantage is temperature independent. Make sure you know that. Mass is also temperature independent. And we don't have to know what the chemical formula of the substance is. So that's an important slide there. But we've already talked about these. All right. Problems get a little bit trickier here. It says rubbing alcohol is a mixture of isopropyl alcohol and water that is 70% isopropyl alcohol by mass. All right. Density is 0.79 grams per milliliter at 20 degrees Celsius. Express the concentration of rubbing alcohol in molarity units and molality units. All right. Let's stop here, work out the problem, and then come back and we'll see if you did this correctly. All right. So the whole thing is to write down these things that are known. Write down the things that are known. All right, welcome back. So down here, they help you out a little bit. You're going to have to do this on your own, but if you've got 1,000, you got a liter of solution or 1,000 milliliters, and the density is 0.79 grams per milliliter, then you have 790 grams of alcohol. We just call it AL, all right, or ALC, all right. And then the molar. Once you get that, you can look at this formula up here. Get the molar mass of that, and the molar mass of the alcohol is 60.09. That's so that's to four significant figures. Yes, this has three. Actually, it only has two. So maybe you didn't need to go that far, but they did. Okay. So now that you had to do on your own. They don't give you that. That's just the setup. This is all the information you're extracting from the problem. So then once you extract the information, let's look at this first problem here. We have 790 grams of, ethanol per solution. Yeah, I'm not as crazy about this, but all right. So what they've done here is 790 grams of ethanol per liter solution, right? And then they said it's a 70% solution of ethanol. Yeah, let's go back. I want to make sure I'm doing that correctly. All right. So they're telling you the density of the solution is 0.79. And yeah, we used this was 1,000 milliliter solution. So this is not the alcohol. This is solution. That is correct. This is the grams of solution that we would have in 1,000 milliliters of solution. Yep. So I made a mistake there. So this is the grams of solution. And so if we go to the next slide. That is correct. It is 790 grams of solution per liter. So that's why we did the density. Okay. And so then they tell us it's 70% ethanol, which means 70 out of 100 grams of solution. And so now we have the grams of ethanol per liter of solution. We can use the molar mass of the ethanol to convert that to moles per liter solution, and now we have the molarity. Works really well. That's the easy one, right? The other one is we have now 790 grams of solution. We know what the mass of the ethanol is. So if we subtract off the mass of the ethanol, that tells us how many grams of water we have, but that needs to be converted to kilograms because molality is moles per kilogram of water, and so the molality is 39 molal. It's a 39 molal 39 molal concentration or a 9.2 molar concentration. That's the way we speak it. Good problem. That's a good problem. You can see again. Here's where we catch the mistake when I made a mistake there. So this is what we do. We look at that and this says solution. If you don't write these units down, these descriptors, then you're going to have a problem. So when I first thought, oh, I'm going to put alcohol here, that's not going to work out. So I have to go back and look at the problem carefully, and it says, no, I've got a liter solution, that's 1,000 grams of solution, and then I have the density of the solution. So what I really have is, even though I've got 1,000 milliliters of solution, only have 790 grams of solution, and that's why this was important up here. So that's what I'm saying. If you don't label this part correctly, you have no shot at it. And then when we say it's 70% ethanol, we're saying it's 70 grams of ethanol per 100 grams of solution. So that's a really important step right there as well. I hope this is helpful. This is where I'm going to stop this video because it's long enough as it is. I hope you're watching it in little pieces, but I do want to do it in chunks through the units. And if you have questions, just email me. Thank you.